Now we've got a thick cable that's 60 feet long and it weighs 180 pounds. You know what? Let's stop right there. 180 pounds divided by 60 feet is going to be 3 pounds per foot. Okay, let's keep going. It's hanging from a winch on a crane. We're going to compute in two different ways the work done if the winch winds up 25 feet of the cable. So here's the crane, here's the cable. So here's my attempt at the pictures that describe this dynamic situation. At the start, we have 60 feet of cable hanging, and if the winch winds up 25 feet of the cable, then we have 35 feet hanging at the end. In the middle, we have X feet of cable, and if this cable weighs 3 pounds per foot, then the weight of this portion of cable is going to be 3x pounds. If I'm moving the cable up from X feet hanging to 35 feet hanging, then at some point I'm going to have to move it from here to here, some incremental distance, delta x. Work done moving it that incremental distance is I'm taking 3x pounds and I'm moving it delta x feet. That of course is going to translate to an integral, so the work is equal to an integral 3x dx. At most we're supporting 60 feet, at least we're supporting 35 feet. These scenarios make the most sense when we put the smaller number as the lower limit and the larger number as the upper limit. Otherwise we get a negative answer. It won't work out. Using the power rule, we get 3/2 x squared evaluated from 35 to, I don't know why I wrote 65, from 35 to 60. That gives a result of 3,562.5. We are in feet now, and so the units are foot-pounds. I know, not very creative. Multiply feet by pounds, you get foot-pounds. Doing it this way makes it feel a whole lot like a spring problem or lifting up a cable that's lying on the ground. Here's our kx dx. This is what makes sense to me, but some textbook authors present this in a slightly different way. Here's another way to look at the same situation. We're cranking up 25 feet of the cable, and at the end of the work that's being done, we still have 35 feet hanging down. So one way to look at it is to say, well, this chunk of 35 feet isn't changing. So let's actually divide the work up into two pieces. One of them is the 35 feet weighs 3 pounds per foot, and that chunk eventually is moving up 25 feet. So we're thinking of that as like a static piece of cable whose length isn't changing, so the force doesn't change, and expressing this as force, that's the weight density of the cable times the length of the cable times distance, plus the part that's being cranked up. It weighs 3x pounds per foot. 3x dx is going to be the like an incremental work, right? An incremental force times distance, really a force times an incremental distance. And at most, this segment of the cable is 25 feet long, and at least that segment of the cable is gone, so it's 0 feet long. And we get 3,562.5 pounds. You'll see that it's the same answer that we got before. I don't particularly like looking at it this way, but it's a valid way to look at it. I think it's much easier if everything that's like this kind of looks the same.